So hello everyone and welcome back to the good stuff we have been doing. Today in this video we're going to try to evaluate, or should I say prove, this integral transformation, and it's called the Cauchy-Schlomilch integral transformation for the German name. And it is quite useful because most of the times when you're trying to evaluate integrals such as integral from 0 to infinity of, say, cosine of ax all divided by x squared plus b squared dx, where this result is e to the negative ab pi to the negative av divided by 2b, I believe. So it is quite useful, and although this result can be proved via contour integration, using contour integration, but this, if you want to do it with real method without having to set up contour, you definitely, this transformation is your best bet towards achieving that. Now the question now is, how do you prove this transformation? How do you prove that the integral from 0 to infinity of what, f of ax minus bx, how do you prove that it equals to the 1/8 as integral from 0 to infinity of f of x squared? Well, to prove it, we are going to first of all note that we can write this always. We can come up here and say, okay, for this expression here, you can take b to be, let's say we are going to, you can take x, so we want to eliminate the b here, so it will be 1/, it will be b, then you divide it. Now you want the a to come up, so you put ay. So you want a to come up, so you take x to be b over ay, and if this is done, you would obtain that dx is going to be negative b over a dy over y squared. Now again, when x is 0, y is infinity, and when x is infinity, y should be 0. So this integral gets to be transformed to become the integral from 0 to infinity of what, f of you get, instead of ax, you get b over y, and instead of minus bx, so b over x will become, okay, 1/ay, right? B over x will become ay, so you have minus ay. Yes, then you have dx, you have b over a times dx over y squared, so that would be b over a times integral from 0 to infinity of, okay, this is a square of f of ay minus b over y all squared, then you have dy over y squared. The reason why I wrote it this way is because there's a square here, so this expression are essentially the same thing, no difference there. Now what do we do next? Well, what you would do here is that you would have to do some combination, because you have these two expressions that first of all, I1 is integral from 0 to infinity of f of ax minus b over x all squared dx, and also I again is still b over a times integral from 0 to infinity of what, f of a, let me use x minus b over x all squared dx over x squared. So if you add the two integrals up, so 2I would be, you would have the integral from 0 to infinity of f of ax minus b over x all squared. Then you will have a 1 plus b over a, b over a times x squared dx. Yeah, so now from here, now you could write this as the you could factor out the a, so you have 1/a times the integral from 0 to infinity of f of ax minus b over x all squared. Then you have a plus b over x squared dx. So now let's take u to be ax minus b over x, then du would be a plus b over x squared dx. So that one is set to. Then what next? When x is infinity, when x is 0 rather, u will be negative infinity. So you have the integral of 1 over 8 from negative infinity. When x is infinite, this will go to 0, this will become infinity. So you have infinity times what? Times you have f of u squared times what? Du. Okay, now this is same thing as twice 2a over integral from 0 to infinity of f of u, let me say f of x squared dx. So if you notice that the 2 cancel out, so basically I would become 1 over 8 times integral from 0 to infinity of f of x squared dx, which is the so-called Cauchy-Schlomilch. I don't know how you pronounce the German name, but that is the transformation. And in the next video we're going to make on this channel, when I'm free, we're going to actually use this transformation to establish this important result in the theory of definite integrals. Okay, we're going to use that to employ it. Now, this result is well known, many techniques to solve it, mostly contour integration, but we're going to use only series and real method to establish the result, and we will be needing this Cauchy-Schlomilch result, which is why I made a video of it first of all. So thank you very much for watching, and please do subscribe to the channel. Thank you and bye.